Hello and welcome to the next lesson here. I'm going to run through a neat activity that we can do in person when we have the equipment in our hands. The smart carts that you've seen me use. We're going to run through an investigation that can be done here, where we can look at the relationship between the angle the ramp's at and the acceleration. So you already saw in more detail the experiment where we looked at the acceleration down the ramp and how it depends on the mass. So keeping the angle the same, just to add more and more mass. And of course, the result was that all objects accelerate at the same rate due to gravity, straight down and also down ramps, regardless of the mass. In this investigation, we're changing the angle though, right? And so if we have the angle at zero, like it's a flat ground, of course you might guess and realize it would be zero acceleration. If we had the angle of the ramp like completely vertical, then it would just be falling straight down, so it'd be your 9.8, right? So we're really looking at the relationship in between, all those angles in between, to see what the relationship is. And so, obviously we can get dt graphs and vt graphs. The slopes of the vt graphs gives us the acceleration, and so we can get these numbers easily enough, right? With the program, with the equipment, I should say. So you would just basically, in a class with a bunch of groups, everybody get a bunch of angles, and we'd sort of start to analyze the data, right? So we end up getting just a bunch of accelerations from the slopes of the VT graphs, from the graphs from the equipment, right? I have a simulation of what those numbers would be. So this table is going to gather 10 data points over 10 seconds. And so right now it's at the zero degrees and zero acceleration. And then, as we're going through a bunch of angles here, okay, so there's a bunch of data, right? And so, if we look at the results we got from class, 3 degrees, it was 1.82. At 3 degree, somewhere between there, anyways, this is calculations of what the acceleration should be. These were experimental results. So I don't know if 20 degrees was close to 3 there in the past. 20 degrees, yeah, exactly, close to 3, right? So just kind of neat to see that the way I'm accelerating these, of course, is based on the actual relationship we're investigating. These are actual just measurements, right? So there's the results that we'd have, and so we're looking for, just trying to see if there's a mathematical relationship between these things, right? And so to investigate a relationship, you can graph it and see if you recognize a pattern, right? So if we graph it and it looks like this, you'd be like, hey, I know that stuff from grade 9. We have a y equals mx plus b kind of a relationship, right? Or if we graph it and it's quadratic, we'd have quadratic skills from grade 10 that would allow us to get an equation. The other way to look at this is actually analyzing the concepts, of course. So we'll see that after the further pages here. The acceleration versus angle result would look kind of like this, and the part that we'll see will be sort of up to that, just because of how the program's made. But if you continued on, this is what it looks like. So it goes to a maximum acceleration of 9.8 at 90 degrees. A minimum acceleration of 0 at 0 degrees, and so on, right? So if you have done this portion of grade 11 math already, you might be really familiar with this shape and recognize it and so on, and know that that's a trigonometric curve, or a sinusoidal curve, right? Curve, the sine function. And so we can see why, okay? And so the idea of the ramp here, the ramp angle, this page is just about what angle in here is the ramp angle. And so if you notice, you've got a ramp angle, 90 degrees, and some other angle. So in this triangle, we've got the 90 degrees, the some other angle, and so this right here must be the ramp angle, right? So this just goes along with the idea of that, right? That you have these two triangles that add up to 180, and then the little triangle has those same two angles and they added 180. So this unknown one here must be that ramp angle. So when we're analyzing this, if we look at the ramp at a really small angle, then if we look at the really small angle, we know there's a small amount of acceleration. And a bigger angle, we've got a bigger acceleration, and an even bigger angle, you got a bigger acceleration. If the angle ramp is 90 degrees, like straight up and down, then the acceleration is 9.8 itself. So what we have is we have this gravity acceleration of 9.8 down all the time, the blue arrow, right? So what we really are getting here, realizing, is that it just makes sense, and I guess is what I'm trying to make obvious to you, is that the acceleration of result down the ramp is the component of the acceleration. So we've obviously seen that you can componentize vectors of velocity and displacement and so on. This is now showing the logic and experimentally confirming that you can componentize acceleration vectors as well. So even in here, really should have, acceleration vector signs over these guys all the time, right? Because it really is a vector. So we can componentize it. So I've got it written as actually I have it written correctly here, right? Where it's the acceleration component vector 9.8, but that's the component is the 9.8 down all the way. And we can see why, right? So when we're analyzing, obviously, sine, cosine stuff, just quick review of SOHCAHTOA here. If you're looking at the opposite side and the hypotenuse, that's sine, right? So sine equals like C over A, for example, opposite of hypotenuse. That's the only part we really need. So we can look at it where we can say, okay, well, this x, this component down the ramp, right, is the opposite side. And the actual acceleration vector, this is the opposite side here. This is the hypotenuse. And so you can see why it's sine, right? As we have the opposite and the hypotenuse. That's why it's sine theta, right? So sine of the angle of the ramp equals the opposite of hypotenuse. And so we end up getting this mathematically, the x component really is this 9.8 sine theta, right? The 9.8 sine theta is exactly what I used in the program to generate these numbers, okay? So basically this is, experimentally the results confirm that it's true, that this logic here, that you can get the acceleration down the ramp by doing 9.8 times sine theta. You're just getting the x component down the ramp. And it works really nicely, which is kind of cool, right? So your 9.8 sine theta curve matches this version here. I need to go this one here, this version of Geometry Sketchpad file. It still works. If you move the angle, you can see the different acceleration values, right? So it goes right up to that value of the, I guess I can do the rest of it to there actually. So so that's your sine, classic sine curve, of course. And that's about it. So basically we have the acceleration down the ramp is a portion of that full 9.8. And I have used this in the past to introduce the idea of components, but I kind of like the way that I went about it here, where it's like we already know about components, and this is just sort of confirming that componentizing acceleration makes perfect sense. The experimental results confirm that everything makes sense, and so on. Right. So that was just a little review of components and so on. I don't have any work for you to do with this one, so I'll leave this one as a no mark associated with it in the on the site or whatever you want to call it in the Dropboxes. All right, so that was just an interest one where you can see like, oh, that's kind of neat that we can do that and the measurements work. So as an activity in class, it's a nice experience or whatever, and I hope you had a bit of that experience as well. All right, so that's it for now. Talk to you later. Nothing needed to be submitted for this one. Remember that. Okay, I'll try and remember it too. See ya.